Come on, there we go.
We are recording. All right, so before I forget about this, the question came up about the master sets, instead of being due on Thursday, be due on the weekend. I think that was the gist of it. I don't have a problem with that. It comes down to your life and how you schedule it, or do I just deal with an individual on an individual basis with that? Any opinions, thoughts?
I think that's good.
So will you submit it online?
Yeah, that's the downside of it, but it'd have to be sent through email. Lawson?
Couldn't we do it like the labs submit over the weekend, cause there's already submission link for that online,
So labs due on the weekend, master sets still due
Thursday?
on Thursday? I'm good with that too.
I know it'd be a good compromise to the paper problem, whether you wanna get
Okay,
one
yeah.
of the master set on paper.
Yeah, all right. So let's officially make labs do, I guess, a little more than a week from when you do the lab. And then when the first test shows up, we'll worry about how we're gonna handle it at that point. All right, so the parallel plate capacitor lab is due Saturday night.
It's fine with me.
All right, but the master set is still due on Thursday. Okay. All right, that's taken care of. All right, any questions from the chapter 25 homework problems?
Number
30? The two very long, thin charged rods lie in the same plane. That one?
30.
One is positive, other is negative. Perpendicular distance between the two rods is r. Find the electric field as a function of little r from up. All right, so this is chapter 25, and actually let's get ourselves some room here. Chapter 25, number 30. We have two rods here, and again, why do I think I'll remember? So this is positive lambda is the charge density. This is negative lambda. This is 0. Those are wires. This would be x equals negative r, and 2r. I think that's electric field as a function of r. So if we're looking at this sort of straight on, we can get into some specifics in a moment. Well, actually, it's an infinitely long wire. What's the electric field of an infinitely long wire?
Do you want it with the epsilon or
Sure, whichever one you give me.
it's lambda over 2 pi r epsilon sine?
All right, and I'm gonna put epsilon first because it's the constant, and then r. So we have a 1 over r relationship for the electric field, and that is, I guess, in the radial direction from the line. So this positive one is exerting an electric field in that direction. The negative one is exerting an electric field acting towards it, and so it's a matter of sort of adding them. So when I am out here, they're in opposite directions. In here, they're in the same direction, and here they're opposite directions again. since the magnitude of the charges is the same, or the linear density is the same, then I know that when R is large, my electric field is small. In other words, in this region right here, this is going to be the dominant one. And when I'm over here, this will be the dominant one. The one that's closer. The one, this is the region where the negatively charged wire is closer to it, so therefore it's dominant. Do you just want a sketch of the graph, or do they want a formula here? Sketch. Well, we may as well do a formula too. So in this region right here, oh, I wrote x equals officially, that's R equals. We've got, let's assume that weight is positive, which I think they've already done, set up that way. And so in this region right here, we've got negative lambda over 2 pi epsilon naught R, plus the electric field coming from here. And so if this is my 0 spot, let's make sure I'm doing this right. So that distance there is R. So that distance would be big R plus little r. So that's the region off to the left. So we'll do a dramatic pause here for questions. In the middle region, they're both going in the same direction. The difference is the distance from here to here, or from here to here, that as one gets bigger, the other one gets smaller. But in this region, from the positive one, we'll have lambda over 2 pi epsilon naught little r. And from the negative one, we have lambda over 2 pi epsilon naught big R minus little r. Because the sum of the two distances has to be big R. And then out here, I've got lambda from the positive charge, lambda over 2 pi epsilon naught R. And from the negative one, minus lambda over 2 pi epsilon naught little r minus big R. So that's roughly what we're sketching right there. Now obviously I got a lambda over 2 pi epsilon naught, assuming that I actually write in the subscript there when I'm supposed to, as a constant, so I'm just going to pull that out. And so what I'm left with is in region 1, I have 1 over little r plus 1 negative plus 1 over big R plus little r. In this middle region, I have 1 over r plus 1 over big R minus little r. And then the right-hand region, I have 1 over little r minus 1 over little r plus big R. So this would be R less than 0, R between 0 and big R, and R greater than big R. And now let's sort of sketch. 0, big R. I guess they went out to 2R. All right, so I got, so R, little r approaches 0, this becomes a constant, and this becomes negative infinity. As little r gets bigger, presumably that's a negative. Let's go ahead and combine. So this is r plus negative mistake there, adding fractions, let's do a quick double check. R over R, big R. So this becomes negative big R over R plus R. And since R is some number here, well, let's try that again. Oh, wait a second. I need to actually settle upon my convention here. I'm so used to R always being a positive number, but the way they've defined it, we're doing this from negative R to positive R. For example, if this is negative 2, here R is, little r would be, say, negative 1. So the distance from here to here is not little r plus r, it's little r minus, it's big R minus little r. I think I got my signs all messed up here. So what I'm gonna do is I'm gonna get rid of my R and put in X because I think I can handle it better. Because this R is not the same as this R. All right, so X equals. So if X is less than 0, so X is a negative number. I know that it has to be going to the left. X would be the distance from 0 to wherever the point in question is, and X is a negative number, so that would work. Over here, this distance would be big R plus that distance, which is negative X, so this is big R minus X. So if X is equal to negative R, then it'd be 2R. Yeah, I'm good with that. Because X is a negative number. So this becomes 1 over X, and then 1 over R minus X. So added together, this would be R minus X. So this is R over X times R minus X, where X is a negative number. So when X is small, that just becomes big R. This thing, the limit as X approaches 0 is negative infinity, because X is a negative number. When X is equal to negative R, the other limit there, I get R over negative R times R minus negative R, which is R over negative 2R squared, which is 1 over negative 2R. So it's that constant lambda over 2 pi epsilon, so not times one over negative 2R. All right. Now, this is something that the theorists do that non-theorists tend not to do, but I know that for this problem, lambda over 2 pi epsilon naught is some constant for the problem. Now, we don't have to know what the unit system is, but I'm going to claim that there is a unit system which exists in which lambda over 2 pi epsilon sub naught is equal to 1. So there exists a unit system where this is true, so let's use that unit system. And so now I can get away with a 1 there. Negative 1 over 2r. All right, questions to here? In this middle region, r is a positive number, so probably was good on that. So this would be x here, or x is a positive number. And this would be r minus x. So 1 over x, 1 over r minus x. Which is the same as that, so this becomes r over x times r minus x. Except x is a positive number. As we approach 0, it is a positive number, but it will shoot off to infinity because what's in parentheses here is roughly equal to r, so that's going to cancel out there, and I'm left with a 1 over, so it's going to look something like this. As I approach r, this approaches a constant, which will cancel out with that r, and this will approach 0 from the positive side, and so we get that. And then the last region, well, that's still x there, and when I'm out here, that distance is x minus r. So it's x minus r minus x over x times x minus r, which is negative r over. And again, we're after the same situation as we are approaching r from the right-hand side. This goes to 0, this goes to r, those are going to cancel out. This is some positive number that is approaching 0, so we're going to infinity, except I got this minus sign out front. So it should look something like that. And we're going out to 2r, I think? Yeah, to 2r. So we get negative r over 2r times 2r minus r, which is negative r over, let's see, that becomes r, which cancels out there, so I'm left with 1 over 2r. That's what I'm seeing. The big thing is take it step by step, think through the directions. Try not to use the same letter to mean 2 different things like I started out doing on this. Continuing my effort to be a role model for things not to do. And somehow my kids picked up some of my bad habits, despite my saying, don't do this. And then I look at the answer just to see that, and that's basically what they had there. They seem to do it more poetically in fewer character strokes than I did. All right, other questions?
Yeah, number 66.
66. uniform electric field passes through a closed surface with a slanted top. Given the dimensions, what's the electric flux through the slanted top? And the electric flux through the entire closed surface. Well, we can do part B quickly. What is the net charge inside the prism?
0.
And therefore, what is the electric field? What is the net electric flux through it?
0.
Yeah. All right, so B is done. Just straight up Gauss's law. Ultimately, you're only going to have a net electric flux through a closed surface if you have an electric field line that goes through once. But if it goes through on one side and comes out the other side, or it goes through one place and comes out another place, the net result is that's not going to contribute to the overall electric flux. Which if you're in Calc 3, I believe you get to at some point. All right, so 66. All right, so let's check out my ability to draw. X, Z, Y. I've done worse. Let's put it in meters just for fun. Do we have anything else? Let's see. Yeah, so I have symmetry. All right, so the electric flux through the slanted top. Absolutely spectacular drawing, I'm sure. So ultimately, when we're trying to find the electric flux, we have a constant electric field, so, well, let's go ahead and do E dot dA. But since the electric field is constant, technically, it's just ultimately going to be the electric field times the area. We factor the electric field is constant, we pull that out, then we're just doing the integral of the area, which is just area. The dot product, so it's magnitude of the electric field times the magnitude of the area times the cosine of the angle between them. So if we pulled a side view of this, so looking at it from this point of view here, then that's 40 degrees there. My electric field,
Is that 40-degree angle given?
yes,
Okay.
yeah, it's in the shaded area right there. And the electric field is in the I direction, which we assume is, I hat direction, which we assume is in the same direction as the x-axis, especially since that's the way they drew it. So 1.57 E for I had newtons per coulomb. And we are trying to find the flux through this surface right here, through that, I believe. Slanted top, okay? So what is the area vector? I'm multiplying two vectors here, my electric field is given to me, but the trick is, what is the area vector?
Well, we know it's perpendicular to the surface.
Okay? Pointing which way?
Is this an open surface?
Ultimately, for the whole problem, it's a closed surface.
Okay. Outward.
You pointing that way? Or this is my surface right here,
Okay, yeah, pointing out that way.
that way. Yeah, that's the way I'm reading it. So we want to know the angle between them when they are tail to tail. So when my area vector is this way and my electric field is that way, that's theta right there. So I need to find that angle. And what is that angle?
That should be 130, right?
Yep. So that's 130 degrees. For those who aren't seeing the 130 degrees, we have this, which is at a 40-degree angle. And Carl will come over for the board. My electric field is that way, my area vector is that way, that's a right angle there. So if that's 40 degrees, that's also 40 degrees. That's a right angle, so 130. So now we have to figure out what is the magnitude of the area vector. Electric field, this is 1.57 times 10 to the fourth. So we need to figure that out. And what are we given here? I know the length is 1.1 meters this way. I know this is 0.5 meters. Do I know anything else? Is this a right angle here? I don't think it says so. What is the electric flux of the slanted top of the surface? I feel like we have to assume that's a right angle there. Am I missing some basic geometry thing? Come on. They are assuming that is a right angle. Let's see, all the electric field lines that enter the top surface also exit the vertical side of the closed surface. Also note that the area vector of the vertical side is parallel to the electric field. That's a right angle. Right angle. I probably should make a note of that. Unless there's somehow
Yeah, I'm not seeing anywhere where it's not getting enough.
So we can find this length right here now, given that's a right angle, of cosine. So I know that the cosine of 40 degrees is 0.5 over the hypotenuse. So my hypotenuse is 0.5 divided by the cosine of 40 degrees. So my area vector will be the length, which is 1.1 meters, times this side right here, the width, which is 0.5 over cosine of 40 degrees. And that should be cosine of 130 degrees there. And someone is about to reveal the answer.
The whole thing or just the 0.5 or cosine 40?
It should be 1.57 times 10 to the 4th times 1.1 times 0.5 divided by cosine of 40 degrees times the cosine of 130 degrees.
It's negative 7,245.
7,265,
45.
45?
Mm-hmm. 0.6.
6.3. 0.63.
Basically, Newton
And
meter squared over Coulomb.
Say it again?
Newton meter squared over Coulomb.
Yep. Now the solution did it slightly differently, but they basically answered B first. Questions on this before we do it the way that the solution did it?